In our last video, we started discussing chemical equilibrium. We are going to continue with that in this video and look at how we can work with our equilibrium constants. So the equilibrium constant, K, and we can use K sub C if we're talking about concentration, or K sub P if we're referring to pressure. If we have a large K, K greater than 1, that means that the products predominate and equilibrium will lie to the right. If we have a K that is less than 1, a small k, that means that equilibrium lies to the left, the reactants predominate. If K is 1, then that means that we are at equilibrium. We have an equal product and reactant. We're going to look at sample exercise 15.3 now. In this exercise, which is on page 638 in your textbook, you have 3 different little squares there, each with 10 spheres. And these little squares represent a container. In the first one, you have 4 red spheres and 6 blue spheres. And the red spheres represent the reactants, the blue spheres represent the products. In the middle box, you have 9 green spheres for the reactants, 1 yellow for the products. And in the third one, you have 2 blue spheres, which are the reactants, and 8 red, which are the products. And the first question asks us to rank these from lowest to highest K. So our ranking would be 2, 1, 3. How do I know this? Well, I can see that in the second container, I have a lot more reactants than I have a small k, because equilibrium is going to lie to the left, the reactants predominate. For 1 and 3, I see I have more product spheres than reactants. So I know that my K has to be larger than 1. And I see that I have 6 products for the first container and 8 for the third container. So that is where I got my ranking. In the second part of the problem, they say, okay, now assume that these containers have a volume of 1 liter and each sphere is going to represent 0.10 mole of that substance. And we are asked to calculate our K sub C for this. So in 1, we have 0.60 mole per liter of our product and 0.40 mole per liter of our reactant. So we will divide, and I just chose here to divide by the number of spheres since each sphere is 0.1 mole. We'll get the same answer. We get Kc of 1.5. In the second one, we have 1 sphere that represents our product, 9 representing our reactants. So our K sub C is 0.11. And then for 3, 8 product divided by 2 reactant equals 4. This matches the ranking that we obtained in our first part of this exercise. This graphic kind of gives you this idea of K. K a lot greater than 1, equilibrium lying to the right, the product side, less than 1 lying to the left. So when we write out our equilibrium constant expressions, when we write it in one direction, we can use the reciprocal of the expression for the reaction written in the reverse direction. And just as a reminder, reciprocal is 1 over. Or we could put, so we put 1 divided by whatever we have determined for that equilibrium constant expression. So that is reciprocal. Okay, we just flip-flop them. The other thing to keep in mind as we are looking at these equilibrium constants and equilibrium constant expressions is that you need to have the associated specific balanced equation. The concentrations of the substance in the mixture are going to always be the same, but the value of Kc depends on how you write the chemical equation because of the exponents. Remember, the exponents in our equation represent the coefficients in the balanced chemical equation. So whenever you are working these, make sure that you always have the balanced equation where you are getting this information. We can also calculate the equilibrium constant for a particular reaction if we know the equilibrium constants for the other reactions that add up to give us that one we want. We did something similar to this when we used Hess's law, where we could look at each part of a reaction and look at the energy change and then calculate the overall energy change based on Hess's law. So we can do the same thing here if we know the equilibrium constants for those elementary reactions that are a part of the overall reaction, then we can calculate the equilibrium constant for our specific overall reaction. So, summary in working with equilibrium constants. So the equilibrium constant of a reaction in the reverse direction is the inverse or the reciprocal of the equilibrium constant in the forward direction. The equilibrium constant of a reaction that has been multiplied by a particular number is equal to the original equilibrium constant raised to a power equal to that number. And the equilibrium constant for a net reaction made up of 2 or more reactions is the product of the equilibrium constants for the individual reactions. So now we can kind of put this together and take a look at sample exercise 15.4, which is on page 640. In sample exercise 15.4, we are now given a couple of reactions with their equilibrium constants, and then we are asked to determine the value of the equilibrium constant for a different reaction. If we look at what these reactions have in common, we can see that we have HF here, and we also have HF in our overall reaction. Notice there's a 2 there, okay? We have, from the first equation, an F minus ion. We have the same thing here, again, with a 2. We also have an H here, which is not in our overall equation, but that's okay. We may find a way to get rid of that for now. But the main difference here is that we have a 2 and a 2, whereas up here we just have 1 and 1. So we're going to need to take this and multiply by 2. Because we need to get those coefficients changed, right? And that's exactly what we do. We're going to multiply each one of those by 2, multiply our K sub C by 2, and we end up with 4.6 times 10 to the negative 7 for the first reaction. Now, if we look at the second reaction that we have up here, we see the H2C2O4 and the C2O4 ion here, but in our overall reaction, you will notice that they are on the opposite sides of the equation. So we are going to have to flip-flop this one, right? We need to look at the reverse reaction here. And so this means that we're going to need to take the reciprocal of this. So we're going to put 1 over 3.8 times 10 to the negative 6. Because remember, the expression is the reciprocal when we go in the reverse direction. And again, that is what we'll do. We will reverse that reaction and say 1 divided by 3.8 times 10 to the negative 6. That gives us 2.6 times 10 to the 5. So now we've been able to manipulate these two equations here to set us up to be able to determine our K sub C of this final reaction. So we'll set these equal to one another, and that gives us this. So remember in our first one, we multiplied everything by 2, and we multiplied our K sub C by 2. And then in the second one, we reversed it, and so we did the reciprocal, and this just is an error in your book. That should be 6 right there, okay? This should be a 6 instead of a 5. But notice now what we're able to do. We can get rid of those hydrogen ions because in our first equation we have it on the product side. Here it's on the reactant side. So we can get rid of those. And now we have the exact equation that we need. Our coefficients are correct. And we have everything that we need, so we just multiply. We multiply our coefficients, and here is our final K sub C for the overall reaction. Now we're moving on to section 15.4, looking at heterogeneous equilibria. Everything that we've looked at so far has been substances that are all in the same phase, usually gases. And when we have an equation that involves substances that are all in the same phase, that is called homogeneous equilibria. If the substances in equilibrium are in different phases, we call that heterogeneous equilibria. You've looked at these terms before. You know that the root word homo means same, hetero means different. So we're going to continue to use those terms here. Where this becomes important is when we look at the heterogeneous equilibria. If we have a pure solid or a pure liquid that is involved in that particular equilibrium reaction, we do not include the concentration of it in our equilibrium constant expression. And there's a couple of ways to kind of think about this. The concentration of a pure liquid or a pure solid is a constant value. So if the mass of a solid doubles, its volume also doubles, right? Because solids have a fixed shape, a fixed volume. When we look at concentration, which is the ratio of mass to volume, then the concentration of the solid would stay the same. So the equilibrium constant expression includes only terms for reactants and products whose concentrations can change. Then the concentration of our pure liquids and solids are omitted. they're not going to change. So we don't even have to consider them as part of our overall equilibrium expression. So when we set up these equilibrium constant expressions for heterogeneous substances, we do it a little differently. We just omit the solids and the liquids. So sample exercise 15.5, which is on page 643 in your textbook, asks you to write the equilibrium constant expressions for two different reactions. When we look at the first reaction, we see that we have water as a pure liquid here. We're not going to include that in our equilibrium constant expression. When we look at our second reaction, we see two solids. We have tin 4 oxide here as a reactant, and then solid tin metal here as a product. Those are also going to be omitted from our overall expression. So when we look at that first one, this is what we have. When we get rid of water and don't consider it in our expression, we only have the carbon monoxide on top, because it is our only product that's left, and then both of our reactants here are on the bottom. And when we look at our second reaction here, because we got rid of the tin 4 oxide and the tin, we only have CO2 on the top and then CO on the bottom. So just keep that in mind when you are writing these expressions. We don't consider pure solids or pure liquids when we are looking at these expressions. Okay, so pure solids, pure liquids, they do not go into our equilibrium constant expression. Now we are actually ready to calculate our equilibrium constants. And we can do this by measuring the equilibrium concentrations of all of the reactants and products in a chemical reaction. We already know how to set up our equilibrium constant expression. Then it's just a matter of plugging everything in. So sample exercise 15.7 wants us to calculate K when we already know our equilibrium concentrations. So we have our reaction here for the Haber process. We've used this one before. We're going to use it again. And when we combine the nitrogen and hydrogen gases, allow them to come to equilibrium, we have 7.38 atmospheres of hydrogen gas, 2.46 atmospheres of nitrogen gas, and 0.166 atm of ammonia gas. And we're going to calculate the equilibrium constant Kp. It's K sub P now because we're looking at pressure. All of our pressure is in atmospheres. Remember, that is one of the components here. Is if you are asked to calculate the K sub P, all of your partial pressures have to be given in atmospheres. If they're not, then you've got to convert them to atmospheres first. So the first step here that we're going to do is set up our expression, which is what we have right here. We've got the partial pressure of the ammonia gas on top. The coefficient is 2. That becomes our exponent. Then we put nitrogen and hydrogen on the bottom. Nitrogen has a coefficient of 1, so that, of course, is understood. And then hydrogen of 3, and so we put that exponent of 3 there. So there is our expression. And now from here, we're ready to just plug everything in from the problem that was given to us. We have the partial pressure of nitrogen here, or I'm sorry, ammonia there, nitrogen here, and hydrogen there, and we simply do the math. And that comes out to 2.79 times 10 to the negative 5. I'm going to use 3 sig figs because that is what was given to me in the problem. And just also as a reminder here, K sub P, K sub C, they do not have units. So when you get your answer here, there's not going to be any unit that is part of it. So that is how we work it out when we know the concentrations. You set up your expression, plug and chug. Okay. But a lot of times we don't know the equilibrium concentrations of all of our species in the mixture. So we can't just do a simple set it up, plug it in, and solve. If we know the initial concentration of at least one of the species, then we can use stoichiometry to deduce the others. So let's look at how we would do that. So first thing is to tabulate all of the known initial and equilibrium concentrations that appear in the expression. So first things first, we're going to look at, okay, what do we know? And then for those that we know, we calculate the change in the concentration as the system is reaching equilibrium. And then we go back to our reaction, looking at the coefficients to calculate the changes in concentration for all of the other species. And this is why having that specific balanced equation is so important. Okay. We can take the initial concentrations from step 1, the changes in concentration for step 3, and calculate any of the equilibrium concentrations that we didn't know from the beginning. And from there, then we can determine our equilibrium constant. So when we don't know the concentrations, we have to do a bit more work to figure it out, to figure out what our concentrations are so that we can set up our expression, plug in the numbers, and go from there. So this is sample exercise 15.8 on page 645 in your textbook. And they tell us we have a reaction vessel that contains 1.000 times 10 to the negative 3 molar hydrogen gas and 2.000 times 10 to the negative 3 molar iodine gas. And we heat that up, and that produces 2 hydrogen monoiodide gases. Okay, 2 moles of that. So they want to know what is the value of the equilibrium constant K sub C if once the system comes to equilibrium at 448 degrees Celsius, the concentration of HI is 1.87 times 10 to the negative 3 molar. So they tell us the concentration of our reactants prior to equilibrium, and then they give us the concentration of the product, the HI, after equilibrium. And so we don't have all of the concentrations that we need here. We've got a couple that are before our initial concentrations. We've got a couple, or we've got one that is after. So we have to figure out what we're going to do. And this is going to involve setting up what we commonly refer to as an ICE table. Okay. ICE stands for initial change equilibrium. So we have the initial concentration, what is the change in concentration, and then what is our equilibrium concentration. So we start with this table, and we're going to plug in what it is that we know. All right. So we have been given our initial concentration for the hydrogen gas and the iodine gas in our problem. Okay, so I'm going to just go ahead and type those in. Okay, and of course we know that this is in molarity, okay? So I type this in from my problem, and at initial concentration, I have no product, right? We can agree that at the very beginning, we have no product. We haven't started the reaction yet. This is just what we're starting with our reactant. So we have 0. So our initial concentration of the hydrogen iodide is 0. Or hydrogen monoiodide, sorry, is 0. All right. Now they also tell us that the equilibrium concentration of the HI is 1.87 times 10 to the negative 3. And at this point, we don't know what the change is yet, and we don't know what our equilibrium concentrations are for the hydrogen and the iodine gases here. Now I've got everything in my table, and I can start filling in the rest of it. Looking at this change here, if I have a concentration of 1.87 times 10 to the negative 3 at equilibrium, and my initial concentration is 0, then I can say that my concentration has increased by 1.87 times 10 to the negative 3, right? I just say 1.87 times 10 to the negative 3 minus 0, and that gives me the exact same, that gives me the change in concentration. Okay. The others, of course, not that straightforward, right? Because they didn't start at 0. So now I have to use my stoichiometry from the reaction to figure out, okay, what then is the change in concentration for the others? So I'm going to take my concentration here of the HI and look at the change in the concentration of HI and relate that to the changes in the hydrogen and the iodine. And this is where, again, that balanced equation is so important. So I take the equilibrium concentration here, and I know that that is moles of HI per liter because it's in molarity. So I'm going to have 2 moles of HI on the bottom. Where did that come from? It came from the balanced equation. 1 mole of H2 on the top because my coefficient is 1. And I'm going to do the same thing for the iodine, right? And so my mole to mole ratio is the same, 2 moles of HI for every 1 mole of I2. So when we do the math here, we see that this is going to be our concentrations here. This is our change in concentration. Okay, so this is our change in concentration. Now, remember that since these are the reactants, the change is negative. I put a positive here to indicate that I have more. I'm producing the product. So each one of my changes for the reactants is going to have to be negative, a negative change. So I'm going to say negative 0.935 times 10 to the negative 3. And they're both the same, so I'm just going to copy this one over here. So now we have our change. We use the change in concentration of our product to determine the change in concentration of the reactants. So now we can calculate the equilibrium concentrations by subtracting. And that's our next step. So we take our initial concentration of hydrogen gas. I'm going to subtract out the change, and here then is my equilibrium concentration, and I'm going to do the exact same thing for iodine. Take the initial concentration minus the change equals my equilibrium concentration. So now I will type that into my ice box. My icebox is complete. Okay, I have my initial concentrations, my change, and now I have all three of my equilibrium concentrations. Now I can actually set up my expression and solve for Kc. So on the top, I'm going to have Hi, and that's going to have the exponent of 2, and I plug in my equilibrium concentration of it, and you'll notice I raised to that power of 2. And then my reactant's going to be on the bottom. I plug in both of the equilibrium concentrations there, and when I do the math, I end up with 51. So this K value is a lot greater than 1. This tells us that equilibrium is going to favor the products. Remember, if K was a lot greater than 1, or greater than 1, but then a lot greater than 1, the equilibrium lies to the right and favors the product side. So equilibrium favors the HI. Okay? So now we've seen two examples. Okay, one where we know all of the equilibrium concentrations and one where we don't. But based on the information we're given and our balanced chemical reaction, we can solve and determine what our equilibrium concentrations are, and then plug it into our expression and solve for the constant. All right. So that's how we can calculate equilibrium constants. Now, the next thing that we're going to look at here is application of the equilibrium constant. So what does it all mean? What can we use this equilibrium constant for? So the equilibrium constant is going to do a couple of things for us. It's going to, number one, predict us to, or allow us to predict the direction of the reaction. Okay. So which direction is it going to go to achieve equilibrium? And then allow us to calculate the equilibrium concentrations of our reactants and products. So the first thing we're going to look at here is predicting the direction of the reaction. And so we have another number that we're going to plug in here. I know sometimes chemistry is like alphabet soup, right? And so we're going to look at what is called the reaction quotient, or Q. Okay, so reaction quotient Q is a number that we can obtain by substituting our reactant and product concentrations, or the partial pressures, into the equilibrium constant expression. Okay, so let's kind of look at our basic equation. So we can write our Q sub C, our reaction quotient in terms of molar concentrations. And here is the expression for that. Now, think of that. You look at that and you're like, that's the same as the equilibrium constant expression, right? And you're right. That expression looks exactly like K sub C. But here is the key, okay? The concentrations used in Q may or may not be the equilibrium concentrations. All right. That is the huge difference here. That even though the expression looks similar, looks the same, we don't necessarily have to use equilibrium concentrations in the reaction quotient expression as we do in the equilibrium constant expression. The equilibrium constant has one value at each temperature. The reaction quotient varies as the reaction proceeds. Because we're not just looking at equilibrium. The reaction quotient is going to vary at the start of the reaction, the middle of the reaction, the end of the reaction. So what do we use K for? Well, we can look at K to determine, is our reaction really at equilibrium? And we can do that looking at and comparing our K values with our Q values. So if Q is less than K, the concentration of the products is too small, the reactants are too large. So the reaction is going to achieve equilibrium by forming more products. If Q is equal to K, then we're at equilibrium. So if Q and K are the same value, then we're at equilibrium. Okay? If Q is greater than K, then that means our concentration of products is too large, reactants is too small, so the reaction has to form more reactants. We have to use that reverse reaction, so the reaction will proceed from right to left. So here is, a graphic that can give us more information about that. So let's take a look at this. All right, so at equilibrium, so if Q and K are the same at equilibrium, or that means that we are at equilibrium, okay? If Q is less than K, we have to get the forward reaction. We have to form more products. If Q is greater than K, we need to go backwards. We've got to use the reverse reaction to form more reactants. So Q can't really tell us a lot on its own. We need to look at the comparison between K and Q. All right. So then we get to sample exercise 15.9. Okay, let's look at sample exercise 15.9 now that I have it copied over here. We're working with our hydrogen iodine reaction again, and they tell us what our equilibrium constant is. It's 50.5. And they want to know in which direction the reaction has to proceed to reach equilibrium if we start with 2 moles, 2.0 times 10 to the negative 2 moles of HI, 1.0 times 10 to the negative 2 moles of H2, and 3.0 times 10 to the negative 2 moles of I2. So when you have a question that looks like this and you need to know the direction in which the reaction proceeds, then you know you're going to have to figure out your reaction quotient. So the first thing that we have to do is figure out our exact concentrations. Think, well, they told us that. Well, they did, but notice that we're not in a 1 liter container, we're in a 2 liter container, and we're dealing with gases. What happens with gases? They expand. So the first thing we have to do is really look at, okay, fine, what is the actual initial concentration? Okay, so we just divide each of those values they gave us by 2 liters. Okay, and that's going to give us our molarity. Because remember, concentration, this is what we're dealing with, has to be in molarity. They didn't give us concentration. They told us the number of moles. They told us the size of the container. We've got to figure out concentration. So here are the initial concentrations. Once we have those, we can plug them into our expression. So here is the expression. Again, it looks just like our equilibrium constant expression, but we're going to plug in the concentrations we were given. So we've calculated those, plugged those in, and our reaction quotient for this reaction is 1.3 at this instant in time. Now, they told us that our equilibrium constant is 50.5. So our reaction quotient is less than our equilibrium constant. So we are right here. Q is less than K, so we need the reaction to move forward. And that was the original question that we were asked. Predict in which direction the reaction proceeds to reach equilibrium. Because Q is less than K, the reaction needs to proceed forward so that we can produce more product. Okay, so we're going to proceed left to right because we have to produce more product. So the reaction proceeds left to right. That would be your answer. Okay, so it's not enough to just calculate QC. You also need to state which direction the reaction is going to proceed. So in this example, then our reaction proceeds left to right. Okay, we need to form more product. Okay, so that's how we can use our reaction quotient there. Now, that's one way that we can use our equilibrium constant. The other way is to calculate equilibrium concentrations. So we need to sometimes calculate the amount of reactant and product that is present at equilibrium in a reaction for which we know the equilibrium constant. And we're going to come back to our ICE tables here. So we're going to use our ICE tables to calculate equilibrium concentrations if we know our equilibrium constant. So let's look at an example here. So we're going to come back to the Haber process. And so now let me just kind of say this. You won't always have to use an ICE table for these. Look at the information that you're given. Don't try to force it into an ICE table if you don't need to. So in this example, we have the Haber process again, and we know our Kp, and we have an equilibrium mixture and the partial pressure of hydrogen gas. We know the partial pressure of nitrogen gas, and we need to figure out the partial pressure of the ammonia gas that has been produced. So we know our equilibrium constant, or in this case, our pressure constant, right? Or our equilibrium constant for pressure. And we're given partial pressure of 2 of the 3. Well, this is kind of going back to what I told you in chapter 14. If you know 3 of the 4 variables, you can always solve for the 4th. So we're going to set up our equilibrium constant expression from the balanced equation. Ammonia on top, exponent of 2 based on that coefficient. Nitrogen and hydrogen on the bottom, coefficient of 1 for the nitrogen, coefficient of 3 for the hydrogen. And we already know what the equilibrium constant is. So we're going to just let X represent our partial pressure of ammonia, because that's what we're solving for. So X is going to be our variable there. So we have X squared over the partial pressure of nitrogen, 0.432, and the partial pressure of hydrogen, 0.928, and we're going to take that to the 3rd power. And we know already that this equals our equilibrium constant that was given to us. So we just have to solve for X. So we'll cross multiply so that we can get X by itself, or X squared by itself. So 1.45 times 10 to the negative 5 times the 0.432 times 0.928 to the cube, and there's our answer. But we're not done yet, because this is X squared, right? Because we had to raise the value of that ammonia gas to the 2nd power. So now we have to take the square root of both sides. So we take the square root of X squared, gives us X. We take the square root of 5.0 times 10 to the negative 6, and that gives us then our partial pressure of the ammonia gas. So they gave us the equilibrium constant for pressure. They gave us the partial pressure of our 2 reactants, asked us to figure out the partial pressure of the product. We had 3 of the 4. We can plug it in and solve for the one that we don't know. So in this example, we didn't have to use an ICE table, right? Now, when we look at our next exercise, we're going to have to use an ICE table. So they tell us that we have a 1.000 liter flask, and we put 1 mole of hydrogen gas and 2 moles of iodine gas, and they give us the reaction, and they tell us our equilibrium constant, and they want to know the equilibrium concentrations of all 3. You think, oh, we already did a problem like this. Well, kind of. In the problem that we had like this before, they gave us the initial concentration of hydrogen iodine and our equilibrium concentration of hydrogen gas. Or, I'm sorry, hydrogen monoiodide. They're not doing that this time. We have the 2 initial concentrations of, or we have the amounts. We don't have concentrations. We have the amounts of our reactants, and we have our equilibrium constant. And they want to know what are the equilibrium concentrations. So we're going to have to use our ICE table. So here is the ICE table for this expression. And the first thing I've got to do here is figure out my initial concentrations. Because they told me I had 1 mole. I have a 1 liter flask. So here my concentration is just going to be, because we're doing mole per liter, remember, for concentration. So I'm just going to have 1.000 for hydrogen and 2.000 for the iodine. Okay. And that's what I know so far, and I know my equilibrium constant is K sub C. All right, so for this one, I have a few more blanks on my table, or in my table. Now I know that, again, for my HI, the initial concentration is going to be 0. Haven't produced any yet. Okay. So now, what do I do? And this is where you kind of have to take a step back and think about, all right, how am I going to solve this problem? So we know that for our reactants, the amount, or the concentration here for our reactants is going to decrease. We don't know by how much, but we know it's going to decrease. Okay. So we're going to plug in an X there because we don't know how much it decreases by. We just know it's going to decrease. Okay. And the same thing here. We don't know how much it's going to decrease by. It's going to decrease by some amount. And we know that our product, our HI, is going to increase by some amount. Well, it's going to increase by the same amount that our reactants decrease, which is 2x. X plus X is 2x. Okay, so our change in concentration is going to decrease for our reactants, hydrogen gas, iodine gas, and it's going to increase by the same amount. Because remember, we're not losing any mass here. We're not losing anything here. So X plus X is equal to 2X. So then our equilibrium concentration then is our initial concentration minus what we lose, minus X. Okay. So for the hydrogen gas, it's 1.000 minus X. For the iodine, it's 2.000 minus X. And for the product, the HI, it's 0 plus 2X, or just 2X. Okay. So we got to figure out, what is X? Okay. When we solve for X, when we figure out what that is, then we've got it. Then we can come back in, plug it in, and then we'll have our answer. Well, how do we solve for X? First thing we've got to do is set up our expression. So we've got HI divided by, or HI squared, okay, because our coefficient is 2, divided by our concentration of hydrogen and iodine. We're just going to plug in what we have in the table, okay? We're just going to plug in the 2X, because that is our equilibrium concentration for HI, and we're going to square that. And then we plug in our equilibrium concentrations for hydrogen and iodine. And they told us in the problem that our Kc for this reaction is 50.5. So we're going to set that equal to 50.5. All right. So there is our expression. We've got it set up. We've got our equilibrium concentrations plugged in there. We know what our equilibrium constant is. So then we cross multiply. Okay. So we act like, this is over 1. So we multiply 2x squared times 1. That gives us 4x squared. And then we're going to say 50.5 times x squared minus 3x plus 2. Well, where'd that come from? Well, that came from multiplying this. So if you remember in algebra with factoring, you say You use the FOIL method. First, outer, inner, last. So you've got your 1.000 times the 2.000, okay? And then you say 1.00 times negative x times 2.000, and then negative x times negative x. So, and then we write it in our standard quadratic method here. X squared minus 3.000x plus 2.00. So here's my 1 times 2, that goes right there. Okay. And then I've got 1.000x, and that's times the negative, so that'd be negative 1.00x. And then I've got plus a negative 2.000x. That gets me my middle piece in the expression. And then x times x, x squared. So I get all of these on the same side of the equal sign. And I'm going to go ahead and multiply by each one of these. And once I do that, get it all on the same side, here is my expression. All right, well, where did this come from? Well, I said 50.5 minus 4. Okay, or 50.5 x squared minus 4, because I've got to multiply it here. And then I said 50.5 times negative 3. That gives me my negative 151.5x. And then I said 50.5 plus 2. That gives me my 101. And then I set that to equal to 0 because nothing's on the other side of the equation anymore. Okay. So here is my equation. This is a quadratic equation where I have x squared, an x, and then not an x here. Okay. So in order to solve this equation, I'm going to have to use the quadratic formula equation. And if you do not remember what that is, okay, in the solving for a quadratic equation, x is equal to negative b, and then plus or minus the square root. Let me get my square root signal. Uh-oh. That's not what I wanted to do. Find my square root. Not one that I use very often, but there's the plus minus. I can go ahead and pop that in so it's not as confusing. Now let me see if I can find my square root sign. Okay, I've got it all typed in there now. I could never find the square root sign. I don't know what happened to it. So here is the quadratic formula. So if you're going to solve this, it's going to be negative b plus or minus the square root of b squared minus 4ac over 2a. So here's what I've got. Here is b, negative, and because the sign comes with it, so negative 151.5. Put that negative in front, okay? Plus or minus my square root, b squared minus 4 times a times c. And I'm going to divide that whole thing by 2 times a. Now, once I do that, I get 2 answers. Because remember, I've got this plus or minus. Okay? Which means I add and then divide, and then I subtract and then divide. Well, here are the answers that I get. All right? Now, I can't, when I look at each of these, Okay, or if I look at both of these, the 2.323 or 0.935, those are my two answers, and I have to decide. When we plug in the x equals 2.323 into our expressions, we get negative concentrations. So if I was to plug the 2.323 in right here and right here, I would get a negative number at equilibrium. Well, I can't have a negative concentration. I can have 0, I can have none, but I can't have a negative number there. So that tells me that this is not a real solution to this problem. So I'm going to go with 0.935. You think, okay, this is getting really complicated. I don't really understand why that makes sense. Well, once you get your two answers here, okay, take them and plug them in right up here in your equilibrium concentrations for the reactants. If you get a negative number there, then that means it is not the solution. So I know that x is going to be equal to this. So now I solve for x. I solve for my concentrations. I plug in x and solve for my concentration. So I'm going to come back up to my table, and I know now that this represents minus 0.935. I'm leaving, normally you would kind of cross this out, but I'm leaving it in here so you can kind of see what I'm doing here. And so I'm going to multiply now here. So when I subtract out my x value of 0.935, then I have, let me do that math here. Zero point 0.065, and over here I'm gonna have 1.065, and here where I'm gonna have 2 times x, that's gonna give me 1.87. So now I have my equilibrium concentrations. Okay, so I have the equilibrium concentrations. That is what I was asked to find, the equilibrium concentrations. I was given the amount, all I was given with to start this problem was the number of moles of hydrogen, the number of moles of iodine, and the equilibrium constant. From that, then I filled out my ice table and I was able to figure out my equilibrium concentrations for each of those. Now, if you want to check your answer, just plug it in, plug it back in, plug what you solved for in here and see, do I get 50.5? And indeed, we get 51 when we plug in our values into the equilibrium constant expression. So therefore, that tells us that our answers are correct. So when you work these problems, just check yourself, plug it back in to your equilibrium constant expression and see, do my answers get me the equilibrium constant I was told in the problem? If you do, if you get really close like this, then you know you have got the correct answers. So that is how you can use ice tables to solve, and the quadratic formula, to solve for your equilibrium concentrations when you're not given at least one of them. Okay, when you're just given your starting concentrations. Now, the last piece that we look at as it pertains to equilibrium concentrations is Le Chatelet's principle. And Le Chatelet's principle was developed by Henry Louis Le Chatelet, and I know I'm butchering that because I'm not French. And he said, if a system at equilibrium is disturbed by either temperature, pressure, or a change in temperature, pressure, or component concentration, the system will shift its equilibrium in order to counteract that disturbance. This makes perfect sense because we said that these are things that can change reaction rates. So it makes sense that they can alter equilibrium. Remember, we're dealing here with gases, right? And we know from our study on gases that temperature and pressure can make a huge difference in the way that gases interact, right? And we also know that by increasing concentration of either our reactants or our product, that can also affect reactions. So the three of those can greatly affect equilibrium. And so if we have a system that is at equilibrium and it is disturbed by any of those things, then we're going to see a shift in the equilibrium. We're either going to see a shift to the right or a shift to the left to counteract the effect of that disturbance. So this graphic here lets us see what will happen. So we change the concentration. So we're either going to add or remove reactant or product. So if a substance is added, then the system reacts to consume some of that substance. If a substance is removed, then the system reacts to produce more of that substance. So let's look at what we've got here. Here we are at equilibrium. Okay, so we've got our reactants, products, and let's say we're going to add more of this blue reactant here. Okay, well, when we add more of the blue reactant and the substances start to react with one another, then we're going to end up probably with upsetting the balance here. So we need these substances to react, right? We need to use up that substance. We added something, we need to use it up. We need to consume it. So we're going to react in the forward direction. And then equilibrium will be reestablished so that we've used up what was added. Okay, so we added a substance here, we added a reactant, so we're going to have the forward reaction here to produce more product because we're consuming that substance. Okay, if we added more product, then guess what? We would perform the reverse reaction because we need to consume some of that. So then we would perform that reverse reaction and go back to some of our individual products or reactants. Now, pressure, if we change, we can change the pressure by changing the volume, right? We know that we have that relationship between pressure and volume. So if we're at a constant temperature, reducing the volume, that causes a shift in the direction that reduces the number of moles of gas. So if we have an initial volume, so here's our initial volume, and we add pressure to that, okay, and now our volume is less than what it was, so we've got to reduce the number of moles of gas. Now, if the temperature changes, so if our temperature is increased, the system acts like we've added a reactant. to an endothermic reaction or a product to an exothermic reaction. So the equilibrium shifts in the direction that it needs to consume the heat. Okay, so if we're in an endothermic reaction and we increase the temperature, the reaction will shift right because we're going to try to use up the heat. So we're going to shift to the right to use up that excess reagent, the heat. If we decrease the temperature, then the reaction shifts left. In an exothermic reaction, if we increase the temperature, the reaction is going to shift left. And if we decrease the temperature, the reaction shifts right. So keep this graphic in mind as you're looking at shifts in reaction when we change the concentration, the pressure, or the temperature. Okay. And here's kind of a summary there of that diagram. And we can look at the rules for the relationship between K and temperature from Le Chatelet's principle. And again, we treat heat like a chemical reagent. So in an endothermic reaction, we consider heat a reactant, and in an exothermic reaction, we consider heat a product, right? Because in an endothermic reaction, it gets colder because it basically sucks in heat from the environment. And then in an exothermic reaction, it is hot because it gives off heat as one of the products. And so when we shift the temperature, then the equilibrium has to shift in a way that it's going to consume the excess heat here, wherever we put it. So our last problem that we're going to look at here is on page 656 in the book. This is exercise 15.12. And in sample exercise 15.12, we're going to use Le Chatelet's principle to predict shifts in equilibrium. So we have a reaction here, and let me get that reaction copied over. So here is the question. We have a chemical reaction at equilibrium, and it says, in which direction will the equilibrium shift when? And they've given us 4 different scenarios here for the shift in equilibrium. So the first one says, in which direction will the equilibrium shift when N2O4 is added? So if we look at that reaction, we see that N2O4 is a reactant. So if we add more reactant, then our reaction or the equilibrium shifts to the right in the direction of the product. So in our first example, the reaction shifts right because we've got to use up some of that N2O4. We've got to use up all of it. So in the first one, the reaction shifts right. We're going to use up the N2O4. We're going to consume it by producing more product. So for the first one, N2O4, equilibrium shifts right. Okay. I said reaction, sorry. Equilibrium shifts right. Okay. So that's the first one. We add more reactant, so we've got to produce more product, so equilibrium is going to shift to the right. So the second one says NO2 is removed. We removed some of the product. So the system adjusts to the removal of the product by shifting to the side that produces more of that product. So equilibrium is still going to shift right. Okay. So we added more reactant. We're going to use it up. Equilibrium shifts right. We took away some of the product. We've got to produce more. So the equilibrium shifts right. The pressure is increased by the addition of N2. So adding N2 increases the total pressure, but you'll notice that N2 is not involved in the reaction at all. So it doesn't affect equilibrium. N2 is not involved. It has nothing to do with this equation, so there is no shift. Okay, no shift. N2, irrelevant to this equation. And then the volume is increased. If the volume is increased, then we're going to shift to a direction where we have a larger volume, so we need more gas molecules. So again, equilibrium shifts right. So volume increased, so we needed more molecules, so we're going to produce more molecules, so it shifts toward the product side. And the last one says the temperature is decreased. So we know from our delta H here, with it being a positive number, that tells us that this is endothermic. Okay. So just based on what we were given in the original problem, we know that this is an endothermic reaction because delta H is positive. So it's an endothermic reaction. So if we decrease the temperature, we have to think about, okay, so where is heat? Where is the heat? So in an endothermic reaction, heat is a reactant, right? That's what we just said up here. In an endothermic reaction, heat acts like a reactant. So if we decrease the temperature, then equilibrium has to shift in the direction that produces heat. Well, where is heat? Heat is a reactant. So in this instance, equilibrium has to shift to the left. Okay, equilibrium is going to shift to the left. Think, okay, I'm totally confused. I don't understand any of this. Please explain it again. Okay, so let's look at it again. So Le Chatelet's principle tells us that we can get shifts when concentration changes, pressure, therefore volume changes, or temperature changes. So in the first example, reactant was added. We have to use up that reactant. So we're going to produce more product. So the equilibrium has to shift toward the product side, which is right. Okay. In the second one, NO2, which is the product, is removed. If NO2 is removed, we have to make more of it. So it's a product, we need more product, so equilibrium has to shift to the right. The pressure is increased by the addition of N2. Well, we look at this reaction, there is no N2. N2 doesn't even exist in this reaction. Completely, just to throw you off here, there's no shift. This N2 has no bearing whatsoever on our reaction. So no shift. The volume is increased. Well, if the volume is increased, then that means we need to generate more moles of the gas. And the way to do that is to make more product. So equilibrium shifts toward the product side, which is to the right. And then our last one, looking at the decrease in temperature, we see delta H there is positive. That means we have an endothermic reaction. And in an endothermic reaction, heat is a reactant. So because we've decreased the temperature, we need to get to the side of the reaction where heat is found, which is on the reactant side. So the equilibrium has to shift left. Okay. So that concludes chapter 15. I hope that this has been helpful for you. and that you have been able to understand more about reaction rate and how we get to equilibrium.